Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired and refreshed. I find my videos interesting and important to your studies. Also, please don't forget to subscribe. Problem 125, consider all losses, determine the discharge in the system. Then also compute the percentage of minor losses to those of major losses. If minor losses were neglected, recompute the discharge. So we are here given a figure for the solution. Take note that the minor losses may be ignored by principle because the condition is when the length of the pipe is more than 1,500 times pipe diameter. For instance, for pipe 1, 1,500 times zero point 0.2 is only 300 meters and the length of the pipe is 900 meters. So supposedly we can ignore minor losses. Same is true with the second pipe, 1,500 times zero point 0.1, 100 mm diameter is 150 meters and we are given 600 meters. So we can actually ignore minor losses. But because the condition of the problem is we have to consider all losses, then we should follow this. Anyway, in the second part, we have to neglect minor losses and expect that the discharge will just increase by a very little amount that the first part, but that the second solution is acceptable rather, disregarding minor losses. So these minor losses consist of entrance loss, which is from the figure flash entrance of zero point 0.5 of the velocity head in pipe 1. Let's call the mean velocity of flow in pipe 1 as V1 and at 2 V sub 2. Then another minor loss here, we have sudden contraction given the loss coefficient for contraction 0.33 times the velocity head in the smaller pipe. That's the rule. And we have submerged exit, which is 1.0 times V sub 2 minus V1 minus V sub B quantity square over 2G, where V sub B, because this is a reservoir, is negligible or zero. And major losses consist of pipe friction 1 and pipe friction 2. We have Darcy-Weisbach friction factor given, Manning's, and for the second part. So by experience, if you write energy equation between points on the water surfaces in the exposed to the atmosphere, then we can show that the head loss is also equal to 15. So 15 is equal to 0.1, 0.5 of velocity head at 1 plus friction loss, which is friction factor 0.02 times length 900 over diameter zero point 0.2 velocity head of pipe 1 V1 square over 2G plus contraction loss 0.33 times velocity head at 2 V2 square over 2G pipe friction, which is 6.35, 0.011 square, length 600, velocity 2 square over diameter zero point 0.1 to the 4 thirds. Then minor loss at the submerged exit 1 times velocity head in pipe 2, 1 times V2 square over 2G. So combining like terms, 15 is equal to 4525 over 981 V sub 1 square plus 10 V sub 2 square. Then by continuity equation to relate V1 and V2, so 200 squared times V1 equals 100 mm squared times V sub 2. I do not show pi over 4 anymore. Anyway, pi over 4 can be cancelled. So expressing V sub 1 in terms of V sub 2, V sub 1 is 0.25 of V sub 2. Substitute into this equation here to solve for V sub 2. So 15 is 4525 or 981 times 0.25 of V sub 2 square plus 10 V sub 2 square. So simplifying further, 15 equals 10.2883 V sub 2 square. From here, we can solve V sub 2, which is 1.2075 meters per second. Then finally, the discharge in liters per second is pi over 4 times 0.1 meter square times 1.2075 times 1000 liters per cubic meter. So discharge is 9.484 liters per second. Then the percentage of minor losses to those of major losses. Minor losses consist of this first term third term and the last term. So 8 sub m is 0.5 of 0.25 times v sub 2 1.2075 square over 19.62 plus 0.33 of 1.2075 square over 19.62 plus 1.2075 square over 19.62. So the minor loss is only 0.1012 meter, and therefore the major loss is, total loss is 15 minus minor loss, so that's the frictional loss. So percentage of minor loss to major loss is 100% times 0.1012 divided by 15 minus 0.1012. So therefore the minor loss is equal to, minor losses percentage is only 0.6792%. In fact, it does not reach 1%. So meaning in the analysis, we can really ignore minor losses. In the second part, we have to ignore minor losses. So therefore, this 15 meters H is equal to the head loss, and the head loss consists only of major losses, which is the second and the fourth terms in this equation. So 15 equals 0.02 times 900 over zero point 0.2 times 0.25 of v sub 2 quantity square over 2g 19.62 plus 6.35 0.011 square 600 v sub 2 square over 0.1 to the 4 thirds. So this is v1. I changed v1 to 0.25 v2 square so that we can solve this problem shortly. So 15 equals 10.219 v sub 2 square. From here, v sub 2 disregarding losses is 1.2116 meters per second, and therefore q prime is pi over 4.1 square times 1.2116 times 1000 liters per cubic meter. So the discharge ignoring losses would be 5.516 liters per second, which is very slightly higher than this considering losses. So that's why this answer is acceptable, neglecting losses. Problem 126. This is similar to the preceding problem, except that the first pipe is smaller compared to the second pipe, and therefore the loss here is due to sudden enlargement, which has this different formula than contraction. So considering all losses, determine the discharge in the system. Assume entrance and exit of pipes are submerged and flush, and that all changes in cross sections are sudden. Recompute the discharge if minor losses are neglected. So for the solution, by experience again, 15 is equated to head loss, minor loss at the entrance, which is loss coefficient 0.5 times velocity head in pipe 1. We call this V1, and pipe 2 plus friction loss 6.35, that's V1, that's V2, 6.35 n square 0.011 square, length 900, then V1 square over diameter 0.1 to the 4 thirds plus sudden enlargement quantity V1 minus V2 square all over 2g or 19.62 plus friction loss Darcy-Weisbach 0.02 times length 600 over diameter 0.2 times velocity head of 2 v2 square over 2g. Then here submerged exit loss 1 times velocity head at 2 or v2 square over 2g. So combining like terms first. So 15 equals 14.92 for V1 square plus quantity V1 minus V sub 2 square over 2G, then plus 3.1091 V sub 2 square. Since by continuity equation, 100 square V1 equals 200 square V sub 2, this time V1 is 4 times V sub 2. So substitute into this equation here. 15 equals 14.924 times 4v sub 2 square plus quantity 4v sub 2 minus v sub 2 quantity square over 19.62 plus 3.1091 v sub 2 square. Simplifying further, 15 equals 242.35 v sub 2 square. From here, we can solve v sub 2. So v sub 2 is 0.2488 meters per second. Then the discharge, considering all losses, is pi over 4 times 0.2, diameter pipe 2 is 0.2 square times velocity 0.2488 times 1000 liters per cubic meter. So the discharge, considering all losses, is 7.816 liters per second. Then for the second part, if we ignore losses, then 15 is equated to the second and the fourth terms only. So 15 equals 6.35.011 square, 900 times v sub 1 square over 0.1 to the 4 thirds plus 0.02 times 600 over 0.2 times velocity head at 2 v sub 2 square over 2g. Replacing v1 by 4 times v sub 2. So v1 14.898 v1 square 3 plus this value 3.0581 v sub 2 square. Replacing v1 by 4 times v sub 2. Then combining like terms, we have 15 equals 241.426 v sub 2 square. So from here we can solve v sub 2, which is equal to 0.2493 meters per second, and the discharge Q prime is pi over 4.2 square times 0.2493 times 1000. So it is expected to increase by a slight amount, so 7.832 liters per second. So that's the reason why we can actually ignore minor losses.